Welcome to today's problem walkthrough. In this session, we'll tackle problem number 1237, find positive integer solution for a given equation. We'll explore the problem requirements, discuss various approaches, and work step by step towards an optimal solution. Let's dive in. In this problem, you're given a monotonic function f, x, y, that returns a positive integer. The key property of this function is that it is strictly increasing with respect to both x and y. This means that as you increase the value of either x or y, the function's output will also increase. For example, if you compare f, x, y with f, x plus 1, y, or f, x, y plus 1, the latter values will always be greater. Your goal is to find all pairs of positive integers, x, y, such that the result of the function equals a given target value z. Additionally, you must ensure that the pairs are returned in ascending order of x, and if there are multiple pairs with the same x, they should be sorted in ascending order of y. The function is defined in the custom function class, which provides the method f, x, y, to calculate the output for given inputs. The input for this problem consists of two components. First, you are provided with an instance of the custom function class, which allows you to evaluate the function f, x, y, for specific values of x and y. Second, you are given an integer z, which is the target value for which you need to find solutions. The output is expected to be a list of pairs of integers. Each pair, x, y, in the output must satisfy the condition f, x, y equals z. The pair should be formatted as a list of lists, such as x1, y1 and x2, y2. Now, let's explore some examples to better understand the problem requirements. Consider the first example where z equals 5 and the function is defined as f, x, y equals x plus y. Here, we need to find all pairs, x, y, such that their sum equals 5. These pairs are 1, 4, 2, 3, 3, 2, and 4, 1. For instance, when x equals 1 and y equals 4, f, 1, 4, equals 5, which matches the target value. Similarly, the other pairs also satisfy the condition. Notice that the pairs are listed in ascending order of x. If there were multiple pairs with the same x, they would further be sorted by y, although that isn't necessary in this case. Now, let's look at another example with a different function. In the second example, the target value is z equals 8, and the function is defined as f, x, y equals x asterisk y, which calculates the product of x and y. To find all valid pairs, we determine combinations where the product equals 8. These pairs are 1, 8, 2, 4, 4, 2, and 8, 1. For each pair, you can verify that multiplying the values results in the target value. For instance, f, 2, 4 equals 8, as does f, 4, 2. Once again, the pairs are ordered by ascending values of x. This ensures that the output format is consistent and meets the problem's requirements. In the third example, the target value is z equals 10, and the function is defined as f, x, y equals 2 asterisk x plus 3 asterisk y. Here, we need to find pairs, x, y, such that 2 asterisk x plus 3 asterisk y equals 10. The only valid pair is 1, 2, since f, 1, 2, equals 2 asterisk 1 plus 3 asterisk 2, which is 10. There are no other pairs of positive integers within the constraints that satisfy this equation. It's important to note that the constraints ensure that both x and y are at least 1, and the monotonicity of the function simplifies the search process by reducing unnecessary computations once the function's output exceeds z. Finally, let's discuss some edge cases. First, consider the smallest possible input values. For example, if z equals 1 and f, x, y equals x plus y, the only valid pair is 1, 1, since 1 plus 1 equals 1. Another edge case is when there are no valid solutions. For instance, if f, x, y equals x asterisk y and z equals 7, no pairs exist because 7 cannot be expressed as the product of two integers between 1 and 1000. Additionally, when dealing with large values of z, such as 10⁻⁴, the solution must efficiently handle the search space without timing out. Lastly, the monotonicity of the function ensures that if f, x, y exceeds z for a given x, there's no need to check larger values of y for that x. This property is critical for optimizing the solution. To begin solving this problem, one of the first approaches we might consider is the brute force method. The intuition here is straightforward. We simply iterate through all possible values of x and y, starting from 1, and check if the function f, x, y, equals the given value z. The steps are as follows. We start with x set to 1, and for each value of x, we iterate through all possible values of y starting from 1. For every pair, x, y, we compute f, x, y, and check if it matches z. If it does, we add this pair to our results. However, this approach is inefficient. Its time complexity is O, n asterisk m, where n and m represent the ranges of x and y, respectively. The main drawback is that it performs redundant calculations and doesn't take advantage of any properties of the function, such as monotonicity, which could help optimize the process. While it's a simple method to understand, it's not practical for large ranges of x and y due to its inefficiency. Now, let's explore a more efficient solution, the two-pointer approach. The key insight here is to leverage the monotonicity of the function f, x, y. Since f, x, y is increasing with both x and y, we can eliminate unnecessary computations. Specifically, if f, x, y is greater than z for a given value of y, increasing x will not decrease the function value. Similarly, if f, x, y is less than z, increasing y will bring the value closer to z. The steps are as follows. We start with x equal to 1 and y set to an upper bound, which is a sufficiently large value. For each pair, we compute f, x, y. If f, x, y equals z, we add the pair x, y to the results, increment x and decrement y. If f, x, y is less than z, we increment x to increase the value of the function. Conversely, if f, x, y is greater than z, we decrement y to decrease the value of the function. We repeat this process until x exceeds a certain upper bound or y becomes less than 1. This approach has a time complexity of O, n plus m, where n and m are the ranges of x and y, and it significantly reduces the number of computations by avoiding redundant checks. By taking advantage of the function's monotonicity, we achieve an efficient traversal strategy. An alternative strategy we could consider is the binary search approach. Here, the intuition is to fix one variable ex, and use binary search to find a corresponding value of y such that f, x, y equals z. The steps are as follows. For each x within the relevant range, we perform a binary search over y to locate the value that satisfies the condition. This approach has a time complexity of O, n asterisk log, m, where n is the range of x and m is the range of y. While binary search is efficient and reduces the number of iterations over y for each x, it introduces a bit more complexity in implementation. Furthermore, given the constraints of the problem, the two-pointer approach achieves a similar level of efficiency while being simpler to implement. As a result, while binary search is a viable alternative, it's not necessarily the most practical choice for this particular problem. Ultimately, the two-pointer approach stands out as the most suitable strategy for this problem. The monotonicity of the function f, x, y is the key insight that allows us to streamline our computations. By moving the pointers intelligently, incrementing x or decrementing y depending on the relationship between f, x, y, and z, we can efficiently find all solutions without the need to check every possible value of y for each x. This approach strikes a balance between simplicity and efficiency. It avoids the overhead of implementing binary search while achieving a comparable time complexity. Furthermore, the two-pointer method directly aligns with the problem's constraints, making it both practical and effective. In summary, this strategy fully leverages the properties of the function to minimize computations, making it the optimal choice for solving the problem efficiently and cleanly. The problem challenges us to find all pairs of positive integers, x, y, such that a given function, f, x, y, equals a target value, z. What makes this interesting is that the function f, x, y is not explicitly provided, and it is nonlinear in nature. To tackle this problem, we'll explore a brute force approach. We start by initializing a variable x to 1. This represents the first input to the function, and will incrementally test all possible values of x. We also create an empty list called result, which will store any valid pairs, x, y, that satisfy the equation f, x, y equals z. The algorithm begins with an outer loop for x, where we systematically increase its value by 1 in each iteration, ensuring that we evaluate all potential candidates for x. For each x, we introduce an inner loop for y, starting at 1 and incrementing by 1 in each step. This nested structure ensures that for every x, we exhaustively explore all values of y, systematically evaluating every possible combination of x, y. Once we have the loop set up, the next step is to evaluate the function f, x, y, using the current values of x and y. We calculate the result of f, x, y, and compare it with the target value, z. If the computed value matches z, we've found a valid solution. We then append the pair, x, y, to our result list. In some cases, if the function f, x, y is monotonic in y, meaning it consistently increases or decreases as y increases, we can optimize the process by breaking out of the inner loop early. For instance, if f, x, y exceeds z and we know the function is strictly increasing, there's no point in continuing further with larger values of y. Additionally, we can introduce a termination condition to prevent infinite loops. For example, if x and y exceed a reasonable threshold without finding any solutions, we can stop the search altogether. Finally, after all iterations are completed, we return the result list, which contains all the valid pairs that satisfy f, x, y equals z. To enhance the brute force approach, there are several key insights worth considering. First, if the function f, x, y exhibits monotonicity in either x or y, we can leverage this property to prune the search space. For example, we could terminate loops early when the function value exceeds z, saving significant computation time. Second, if f, x, y is symmetric where f, x, y equals f, y, x, we can reduce redundant calculations by only exploring one half of the search space. This symmetry allows us to skip evaluating duplicate scenarios. Additionally, if valid solutions to the equation are sparse, the brute force method might be computationally expensive. In such cases, analyzing the properties of f, x, y to refine the search space is crucial. From a data structure perspective, we use a simple list to store valid x, y pairs. This is efficient since we only need to return a collection of pairs. The computational complexity of this brute force approach is n squared, where n is the maximum range of x and y. This results from evaluating every combination of x and y. A space complexity, on the other hand, depends on the number of valid solutions, making it s, where s is the size of the result list. It's important to consider edge cases when implementing this algorithm. For instance, if no pair x, y satisfies the equation f, x, y equals z, the algorithm should gracefully return an empty list, indicating no solutions were found. On the other hand, if multiple pairs satisfy the condition, the algorithm must ensure that all valid pairs are included in the result. For large values of z, the brute force approach may become computationally expensive. In such scenarios, optimizations like early stopping or leveraging properties such as monotonicity or symmetry are essential to improve efficiency. Another critical consideration is how the algorithm handles negative or non-integer inputs. If x, y, or z can be negative or non-integer, the algorithm must be adapted accordingly, such as adjusting the range of loops or handling edge cases for the function f, x, y. By carefully addressing these edge cases, we ensure that the algorithm is robust and capable of producing correct results under a variety of conditions. The given problem asks us to find all positive integer pairs, x, y, such that a hidden function f, x, y equals a target value z. The function f, x, y is monotonic in both x and y, non-decreasing with respect to increasing inputs. This property allows us to optimize the search process. Explanation of the code. 1. Custom function class. This represents the hidden function f, x, y provided by the system. The implementation is not visible to us, but we can call it using custom function.f, x, y. 2. Solution class. The find solution method is implemented to compute all valid pairs, x, y, where f, x, y equals z. 3. Initialization. We initialize x to 1, the smallest possible value, and y to 1000, the largest possible value, given the problem constraints. For two-pointer technique, using a while loop, we explore the solution space. We compute the value of f, x, y. If f, x, y equals z, it means we found a valid pair. We append the pair, x, y, to the result and adjust both x and y to continue searching for other solutions. If f, x, y, z, we increment x to increase the function value. If f, x, y, z, we decrement y to decrease the function value. 5. Termination. The loop terminates when x greater than 1000 or y less than 1, ensuring the search stays within valid bounds. 6. Output. The result list containing all valid pairs is returned. ###efficiency. This approach is efficient due to the monotonicity of the function. Instead of iterating through all possible values of x and y, which would take n squared time, we use the two-pointer technique to achieve a much faster solution with time complexity closer to n. This is because each adjustment of x or y reduces the solution space significantly. ### edge cases. If z is smaller than the minimum possible value of f, x, y, the result will be empty. If z is larger than the maximum possible value of f, x, y, the result will also be empty. The algorithm handles these cases naturally since the loop will terminate without finding any pairs. Here, we start by importing the necessary utilities and defining the custom function interface as described in the problem. This interface includes a method f, which takes two integer inputs, x and y, and returns a result. The exact implementation of this function is hidden, but we know that it is monotonic, meaning it either consistently increases or decreases as the inputs change. In the solution class, we define the method findSolution, which takes an instance of custom function and a target integer z. Our goal is to find all pairs of positive integers x and y such that f, x, y equals z. To achieve this, we initialize a list called result to store the valid pairs. We also set up two pointers. X starts at 1, representing the smallest positive integer, while y starts at 1000, which is the largest possible value according to the problem constraints. We then use a while loop to iterate as long as x is less than or equal to 1000 and y is greater than or equal to 1. Inside the loop, we calculate the value of f, x, y using the function provided. If this value matches z, we add the pair x, y to the result list and adjust both pointers by incrementing x and decrementing y. This ensures we continue searching for other potential solutions. If the value of f, x, y is less than z, it means we need a larger result, so we increment x to explore higher values for the first parameter. Conversely, if the value of f, x, y is greater than z, we decrement y to lower the result, as the function is monotonic. By adjusting the pointers in this way, we ensure that we efficiently explore all potential combinations without unnecessary computations. Once the loop has finished running, we return the result list, which contains all the valid pairs of x and y that satisfy the equation f, x, y equals z. This two-pointer approach ensures optimal performance while adhering to the problem constraints, making it both efficient and easy to understand. In this problem, we need to find all pairs of positive integers, denoted as x and y, that satisfy a given equation f, x, y equals z. The function f, x, y is provided by a custom function class, and while we don't know its exact implementation, we do know that it is monotonically increasing with respect to both x and y. This means that as x or y increases, the value of f, x, y also increases. Additionally, the inputs x and y are constrained to be between 1 and 1000 inclusive. As an example, let's consider a case where the target z is 5, and the function is defined as f, x, y equals x plus y. We start with x equals 1 and y equals 1000. Calculating f, 1000, we get 1001, which is greater than our target z. To reduce the value, we decrement y. This process continues until y equals 4, giving f, 4 equals 5, which matches our target. We add the pair 1, 4 to our result. Next, we increment x to 2 and reset y to 1000, repeating the process. However, no additional pairs satisfy the condition for this target. Thus, the final result for this example is 1, 4. Now, let's take another example where the target z is 10, and the function is defined as f, x, y equals x asterisk y, meaning the product of x and y. We start with x equals 1 and y equals 1000. Calculating f, 1000, we get 1000, which is much greater than our target. To reduce the value, we decrement y until it equals 10, where f, 10 equals 10. This matches our target, so we add the pair 10 to our result. Next, we increment x to 2 and reset y to 1000. Evaluating f2, 1000, we get 2000, which is still greater than the target. We continue decrementing y until it equals 5, where f2, 5, equals 10. This also satisfies the condition, so we add 2, 5 to the result. Incrementing x again to 3 and repeating the process, we find no additional pairs that meet the condition. Therefore, the final result for this example is 1, 10, 2, 5. Finally, let's consider an example where the target z is 25, and the function is defined as f, x, y, equals x squared plus y squared. The sum of the squares of x and y is starting with x equals 1 and y equals 1000. We calculate f, 1, 1000, which results in a very large value, much greater than our target. To narrow the search, we decrement y systematically. Eventually, when y equals 5, we calculate f, 1, 5, equals 1 squared plus 5 squared equals 26, which is still greater than 25. Continuing this process, we increment x to 3 and evaluate f, 3, 4, equals 3 squared plus 4 squared equals 25, which matches our target. We add the pair, 3, 4, to the result. Further exploration reveals no additional pairs satisfying the condition. From these examples, we can observe that the monotonicity of f, x, y allows us to use a two-pointer-like strategy to reduce redundant calculations. By adjusting y when the value is too high and incrementing x when the value is too low, we efficiently narrow down the search space. The constraints, where x and y are bounded between 1 and 1000, ensure that this approach terminates quickly. The final outputs are 1, 4 for the first example, 1, 10, 2, 5 for the second, and 3, 4 for the third. Now, let's analyze the time complexity of this solution. The algorithm operates with a two-pointer-like approach, starting with x equal to 1 and y equal to 1000. In each iteration, the function evaluates custom function.f, x, y exactly once. Based on this evaluation, it adjusts the pointers either incrementing x, decrementing y, or both when a solution is found. The key observation here is that each pointer can only move a maximum of 1000 steps. This means that x increases up to 1000, and y decreases down to 1, resulting in a total of at most 2000 moves combined. Therefore, the time complexity is O, n plus m, where n is the maximum value of x and m is the maximum value of y. Given the constraints of the problem, n and m are both 1000, so the complexity simplifies to O, 1000, which is highly efficient for this input size. Next, let's consider the space complexity. The algorithm uses a list called result to store all valid solution pairs of x, y. The size of this list depends on the number of solutions k that satisfy the equation custom function.f, x, y equals z. In the worst case, if every combination of x and y produces a valid solution, the size of result could theoretically grow to be proportional to n multiplied by m. However, due to the monotonic nature of the function, this scenario is extremely unlikely. The problem constraints further ensure that k, the number of solutions, is at most 1000. As a result, the space complexity is O, k, where k is significantly smaller than n asterisk m in practice. Let's compare this optimized approach with a brute force method. A naive approach would evaluate custom function.f, x, y for all possible pairs of x and y, iterating from 1 to 1000 for both variables. This would result in a time complexity of O, n asterisk m, or O, 1000 by 1000, which equals O, 10 to the power of 6, evaluations. On the other hand, our optimized two-pointer approach leverages the monotonicity of the function to reduce the number of evaluations to O, n plus m, which is far more efficient. For space complexity, both approaches are identical, requiring O, k, storage for the list of results. Additionally, analyzing best, average, and worst cases shows that the optimized algorithm consistently evaluates at most n plus m pairs of x and y, even when z is large or the solutions are sparse, maintaining a bounded O, n plus m, time complexity. Finally, let's summarize the mathematical reasoning behind the big O analysis. The two-pointer approach ensures that each pointer moves at most n or m steps. Since each iteration involves constant time operations such as evaluating custom function.f, x, y, performing comparisons, and updating the pointers, the total time complexity is directly proportional to the number of iterations, which is O, n plus m. For space complexity, the result list grows proportional to the number of valid solutions k. This means the algorithm requires OK space. Overall, these characteristics make the two-pointer approach both time-efficient and space-efficient for solving this problem within the given constraints. One of the most common mistakes when solving this problem is not considering edge cases. For example, if the function f, x, y involves division, failing to handle situations where the denominator is 0 can lead to runtime errors. This often happens because we focus on solving the general case and overlook boundary scenarios. To avoid this, make it a habit to test edge cases explicitly. For instance, check the smallest and largest possible inputs, or situations where certain operations, like modular arithmetic, might break. Another frequent issue is relying on inefficient brute force implementations. Iterating through all possible values of x and y without applying any constraints or bounds can lead to unnecessary computations and even timeouts in competitive programming. The solution here is to analyze the problem constraints, impose logical bounds, and break out of loops early when conditions are met. Another pitfall is using incorrect termination criteria. For example, implementing a loop with a condition like while true but failing to include a proper break condition can result in infinite loops. This often happens when the stopping condition of the algorithm hasn't been clearly defined up front. To prevent this, always determine how your loop should terminate before you start coding. Overlooking numerical overflow is another common mistake, particularly in problems with large inputs. Intermediate values of x or y can exceed the range of integers in some programming languages. To address this, use appropriate data types, like long in Java or Python's arbitrary precision integers, and ensure you test with large edge case inputs. Finally, misunderstanding problem constraints can lead to incorrect solutions. For instance, assuming x and y must be distinct when the problem allows x to equal y. This usually stems from misreading or skimming through the problem statement. Always take the time to carefully read and annotate the constraints to avoid this issue. In an interview setting, recognizing patterns in problems involving f, x, y can be a game changer. For example, if f, x, y equals x multiplied by y, you might notice that f, x, y is symmetric, meaning f, x, y equals f, y, x. This observation can help you reduce the solution space significantly. Another key strategy is to analyze trade-offs between brute force and optimized approaches. While brute force is straightforward, methods like binary search can reduce complexity but require a sorted search space. It's also important to clarify any ambiguous constraints during an interview. For instance, ask whether x and y are bounded or if x must always be less than or equal to y. Starting with a brute force approach is often a good strategy, but make sure to propose optimizations during your explanation. This can include techniques like pruning the search space or leveraging mathematical insights to refine your solution. This problem shares similarities with several related problems that can help you build a deeper understanding. For instance, LeetCode 1-2 sum is a classic pair finding problem involving constraints. Similarly, LeetCode 454, for sum 2, focuses on finding tuples where a function of the elements equals a target value. LeetCode 263, ugly number, leverages relationship properties to determine if a number can be expressed as a product of specific factors. Finally, LeetCode 149, max points on a line, involves iterating over pairs and analyzing relationships, which parallels the structure of f, x, y problems. When it comes to alternative approaches, one option is optimized brute force. By carefully imposing limits based on problem constraints, such as breaking early if f, x, y is monotonic, you can reduce unnecessary computations. This method is simpler to implement but can still be slow for very large inputs. Another approach is binary search, which is effective for problems where f, x, y is monotonic in one of the variables. However, it requires careful implementation and sometimes pre-processing, like sorting the search space. Hashing is another powerful alternative for solving this type of problem. By pre-computing values of f, x, y, and storing them in a hash map, you can achieve faster lookups for repeated queries. The trade-off here is higher memory usage, but the speedup can be significant, especially for problems involving multiple queries. Another advanced technique is using mathematical simplifications. For instance, analyzing the properties of f, x, y, such as linearity or modular arithmetic, can help reduce the problem size and eliminate unnecessary computations. This approach often requires a deeper understanding of mathematical concepts, which might not apply in all scenarios but can be extremely effective when it does. Both of these methods highlight the importance of adapting your approach to the problem's specific constraints and properties. Thank you for joining this session. To recap, we discussed the brute force approach for finding positive integer solutions and analyzed its trade-offs. Remember to practice similar problems to strengthen your problem-solving skills. See you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!